Hello everyone, my name is Aditi Sunil Kalmegh. I am student of Shri Shivaji Science College Amravati. My today's seminar topic is the nuclear models. Introduction. The nuclear shell model. Inspiration for developing shell model of nucleus was derived from a very successful electronic shell model of atom. An electronic shell is completely filled when it contains a certain definite numbers of electrons. An atom with closed shell electronic configuration is very stable and exhibits chemical inertness. In the nuclear world, it was observed that nuclei with 2, 8, 20, 50, 82, and 126 protons or neutrons or both exhibit exceptional stability associated with these numbers. These were called as magic numbers. Today we have explanation in terms of nuclear shell model, but still the name continues. In 1948, this model was mathematically developed by Mayer, Jensen, Hexel, and Swiss by applying quantum mechanics on the basis of certain assumptions, that is postulates. So first we discuss about postulates of shell model. Each nucleon moves in its own orbit, which is determined by the nuclear potential. Nucleons are distributed in a series of discrete energy levels. As the capacity of each orbit is reached, a closed shell is formed. A proton forms a pair with a neutron. Similarly, a neutron forms a pair with a neutron, and a proton cannot form a pair with neutron. In case of odd neutron or odd proton or both nuclides, the nuclear properties like speed, parity, and magnetic moment are due to the presence of unpaired nuclei. This model is mainly applicable in the ground state of the nucleus. This is the figure of nuclear energy levels in a shell model. Now, evidences for the existence of magic numbers. Helium with mass number 4, calcium with mass number 40, and oxygen with mass number 16, that is 8 proton and 8 neutron, are highly stable in comparison to close neighbors. We may thus conclude that the numbers 2, 8 and 20 indicate higher nuclear stability. There is a group of isotopes with capital N equals to 82, means 82 proton, 82 neutron, and which are highly stable. Other groups of isotopes with neutron 20 and neutron 50 are also highly stable. Thus 20, 50 and neutrons 82 are also indicate higher nuclear stability. Tin with atomic number 50 has 10 stable isotopes. Similarly, calcium with 20 protons exhibits 6 stable isotopes. This means that the numbers 20 and 50 are associated with higher nuclear stability. There is a good deal of experimental evidence to show that the numbers 2, 8, 20, 50, 82 and 126 called as magic numbers for either proton or neutron are associated with higher nuclear stability. For example, the isotopes with the proton or neutron means here the neutrons are 9, or when neutrons are 51 and neutrons are 83, spontaneously emit a neutron each to acquire stability with neutron 8, 50 and 82 respectively. It has also been found that if some of the important nuclear properties are plotted against proton or neutron, the graphs show distinct peaks or troughs at numbers 2, 8, 20, 50, 82, and 1 to 6. The above numbers are thus called magic numbers for nuclear shells and correspond to closed nuclear shells. In all the natural radioactive decay series, the ultimate end products are the isotopes of lead, indicating greater stability associated with 82 protons. Energy required to remove 126th neutron from Pb is 7.36 megaelectron volt, while for 127th neutron from 209 Pb is only 3.87 megaelectron volt, which indicate higher stability corresponding to 126th neutron. Heaviest stable nuclide in nature is bismuth, which shows that 126 neutrons form a stable closed shell. Now, advantages of shell model. The main success of shell model is the explanation of magic numbers. Stability of elements can be predicted. Third, it gives theoretically correct values of magnetic moment. This model is capable of predicting ground state nuclear spin. The shell model explains nuclear isomerism. The shell model can easily explain the periodicity observed in nuclear properties. Now we will discuss about the limitations of shell model. So first, shell model fails to explain stability of hydrogen, lithium, beryllium and nitrogen, boron and nitrogen. It fails to explain nuclear fission. This model is unable to explain the formation of compound nucleus. The observed cross sections of nucleus with high energy particles cannot be explained by this model. Now we will discuss about the second model, that is liquid drop model. Liquid drop model is statistically in nature and was developed by N. Bohr and J. Wheeler in 1936 and independently by Franklin on the basis of certain assumptions. Postulates of liquid drop model. Nucleus is a homogeneous entity consisting of certain number of protons and neutrons. Each nucleon interacts strongly with its neighbors. Consider the collective motion of all nucleons. The interaction force, that is the nuclear force, is assumed to be a short range and one tending to saturation. Thus, nuclear force is similar to intermolecular force of attraction in liquid drop. Nuclear force is independent of charge and speed of the nucleons. Behavior of nucleus is comparable to that of a liquid drop. This is the comparison of the nucleus with that of the liquid drop. Here, the liquid drop is consist of large number of molecules and in nucleus consist of all nucleons. Now we will discuss about advantages of liquid drop model. It provides basis for the equation of Weizsäcker for calculating the accurate binding energies of nuclei and hence their atomic masses. Radioactive decay could be predicted correctly. It could explain a nuclear fission reaction. It explains the mechanism of low energy nuclear reactions. It predicts alpha and beta emissions properties. Capable of explaining nuclear properties in excited state. Some limitations of liquid drops are there. Liquid drop models are there. These are as follows. The periodicity in nuclear properties at magic numbers of protons and neutrons does not find any satisfactory explanation in this model. It fails to explain the stability of heavy nuclides. This model is not consist of with the PP or NN pairing effects which are prominently observed in stable nuclei. The model ignores independent motions of nucleons, magnetic moment effects, etc. The application of the model is limited to the nuclei with the medium mass. In light nuclei, most nucleons are on the surface, whereas in heavy nuclei, Coulombic effects cannot be entered. Liquid drop model and nuclear fission. Bohr-Wheeler theory of nuclear fission. The liquid drop model can explain the phenomenon of nuclear fission. A liquid drop has a spherical shape due to internal molecular forces responsible for surface tension. On applying a large external force, the sphere may change into ellipsoid. If the external force is sufficiently large, ellipsoid may change into a dumbbell shape and may even break at the narrow 8 into two portions. According to Bohr-Wheeler theory, the nucleus behaves like a drop, liquid drop. When the nucleus captures a neutron falling on it, it forms a compound nucleus which is highly energetic. The extra energy may set up a series of liquid oscillations in the spherical compound labeled as A in figure below. As a result of this oscillation, the shape of the nucleus may change at time from spherical or ellipsoid labeled as capital B in the same figure. If the extra energy is large, oscillations may be so violent that stage C and ultimately stage D may be approached. The nucleus is now dumbbell shaped and both parts of the dumbbell, which are not necessarily of equal size, carry positive charge. The energy required to change the nucleus from stage A to stage D is called as fission barrier. The nucleus is now in critical state because once stage capital D is reached, the final fission into fragments, that is stage E, is inevitable on account of repulsion between the two fragments. This is the figure of the liquid drop model and the nuclear fission. So thank you very much.